Hello and welcome to Sleep Science. It's a pleasure to have you here. Before we begin, I'd love to know where in the world you're listening to us tonight. From a quiet room on a sleepy train ride, or perhaps from a cozy couch with a hot cup of tea, wherever you are. I hope you feel comfortable, safe, and ready to gently dive into your thoughts. If you enjoy these relaxing explorations and would like to hear more, leaving a like and subscribing really helps this little channel grow and reach more people passionate about science. And for those of you who are already subscribed, thank you, truly. Your support means more than you can imagine. Now, I'll try not to make tonight's topic so interesting that it keeps you wide awake. But if that happens, at least you'll have a better understanding. Why particles sometimes act like waves, and why accepting that even someone is observing is a small price to pay for a restless night. So let's begin. What is quantum physics? And why does it so often sound like the universe is making things up as it goes along? The world we know, the one we can see and touch, seems solid, predictable. If you knock over a teacup, it falls. If you toss a coin, it lands. If you close your eyes, the moon doesn't disappear. But in the early 20th century, scientists began to look more closely, much closer. And the deeper they delved into the workings of matter, the stranger things became. Light, they discovered, could behave as both a wave and a particle. Particles, in turn, could exist in many places at the same time until they were measured, and the act of observing something not only revealed what was already there, but seemed to change it. This wasn't a quirk of bad data or inaccurate equipment. It was real, reproducible, and broke the orderly laws of classical physics that had held sway for centuries. Quantum physics wasn't just a new branch of science, it was a new way of seeing reality. A strange, shimmering reality where certainty gives way to probability, and cause doesn't always precede effect in the way we expect. In this video, we'll float gently through this world. There's no need to understand every equation or memorize every name. Let's move slowly, gently, one mystery at a time. From the first puzzles that knocked scientists off their classical pedestal to the modern questions that still keep physicists awake at night. So, curl up, close your eyes if you like, and let's begin exploring a world where even the void isn't really empty, and where everything you thought you knew about reality is only probably true. At the turn of the 20th century, physics seemed nearly complete. The laws of motion were understood, thermodynamics was well organized, and light was comfortably nestled within the framework of electromagnetic theory. It was a golden age of certainty. Some scientists even believed that all the big questions had already been answered. There were only a few oddities left to clean, like dust in the corners of a well-swept room. One of those dusty corners involved a very simple idea. What happens when you heat an object? When you heat a piece of metal or a lump of coal, it glows first red, then orange, then white, depending on the temperature. This glow, called black-body radiation, comes from how objects emit electromagnetic radiation when heated. It was easy to observe and seemed like it should be easy to explain, and yet mathematics refused to cooperate. Classical physics, using the well-known equations of the time, predicted something bizarre. According to the formulas, as a black body's temperature increased, it should emit more and more energy at increasingly shorter wavelengths, particularly in the ultraviolet range. The problem with this prediction was that it led to infinite energy at high frequencies, a scenario so impossible and ridiculous that it was dubbed the ultraviolet catastrophe. No tweak to the classical equations could prevent the mathematics from collapsing. Reality simply didn't match predictions. Something was missing. Enter Max Planck in 1899. Planck was a German theoretical physicist with a reputation for careful thinking. He wasn't particularly radical or rebellious. In fact, he firmly believed in the classical worldview, but he was also pragmatic, and when faced with the problem of black-body radiation, he did something quietly revolutionary to fix the math. Planck introduced a small, strange idea. What if energy couldn't be emitted in any quantity? What if instead it came in tiny, indivisible packets, like coins you couldn't split in half? These packets would represent the smallest possible units of energy. He called these packets quanta, This was a drastic departure from the continuous view of energy in classical physics. Instead of a smooth flow, the energy would arrive in steps, tiny jumps, that depended on the frequency of the radiation. Planck even introduced a constant, now known as Planck's constant, to describe the size of these energy packets. It was unimaginably small, but mathematically elegant. When he inserted this idea into his equations, something incredible happened. The infinite energy problem disappeared. The equations worked. They corresponded to the real world. Planck had solved the ultraviolet catastrophe, and yet he didn't fully believe it. In fact, Planck himself described his solution as a mathematical trick, a clever way to make numbers behave, but not a description of how the universe actually worked. He assumed that future physicists would find a better explanation that didn't require such strange assumptions. Quantization for him was a temporary fix, not a fundamental truth. What he couldn't have known at the time was that his trick would become the cornerstone of an entirely new way of thinking. His idea that energy comes in discrete packets paved the way for quantum theory, a theory that would soon unravel much of what classical physics had taken for granted. It's easy to look back and see this as the moment everything changed, but at the time, it seemed more like a strange footnote than a revolution. Planck didn't set out to challenge the foundations of physics. He just wanted the math to work, and yet by introducing quantization, he lit the first match in what would become a slow-burning fire, one that would eventually reshape our understanding of light, matter, and the nature of reality itself. This humble beginning, hidden in a quiet article published in 1900, didn't scream its importance. There were no dramatic statements, no grand pronouncements, just a small constant, a new way of thinking about energy, and a small curious fix for a problem that refused to go away. From that point on, physics would never again seem complete. In the early 1900s, light was thought to be well understood. Thanks to James Clerk Maxwell's equations, scientists had shown that light behaved like a wave, an elegant ripple in the electromagnetic field. It bent, reflected, diffracted, and interfered as any wave should. And after Max Planck's quiet introduction of energy quanta, most physicists assumed things would settle down into a new, slightly adjusted normal. But then came a conundrum involving metal, light, and a surprising refusal to cooperate. It was called the photoelectric effect, and it worked like this. If you shine light on a metal surface, electrons can be ejected from the metal. The idea made sense. Light delivers energy. Energy expels electrons. No big deal. According to wave theory, increasing the brightness of the light should increase the energy transferred to the electrons. A brighter wave should knock electrons loose more efficiently. That was the expectation. But that wasn't what happened in experiments. Scientists discovered something strange. Shining brighter light didn't necessarily eject electrons with more energy. What mattered most was the frequency of the light. If the light was below a certain frequency, even very bright light did absolutely nothing. No electrons were ejected, but above that frequency, even a weak beam could easily knock electrons off. The threshold was sharp and made no sense. Under classical wave theory, this small inconsistency became a complete mystery. Enter Albert Einstein. In 1905, a year often referred to as his miracle year, Einstein published a paper that changed everything by explaining the photoelectric effect. He proposed something bold. What if light wasn't just a wave? What if, under certain circumstances, it behaved like a particle, a tiny packet of energy? Traveling in a straight line, Einstein suggested that light was made of individual packets of energy, which he called light quanta. Later, these packets would be known as photons. Each photon carried a specific amount of energy determined by its frequency. If a photon had enough energy, it could knock an electron off a metal surface. If it had no photons at all, no matter how many or how brilliant they might be, the work wouldn't get done. It was like trying to open a locked door with a handful of keys, none of which fit. Einstein's idea was based directly on Planck's earlier work, but it went further. He wasn't just using energy packets as a mathematical trick. He was suggesting that light itself was made of these packets, not as a convenient fiction, but as a literal description of how light behaves. It was a revolutionary claim, and not everyone liked it. Many physicists clung firmly to the wave model of light. After all, light clearly exhibited wave-like behavior. It diffracted around corners, creating interference patterns. If light were truly made of particles, how could it also behave like a wave? Einstein didn't deny the wave nature of light. Instead, he proposed something stranger. Light, he said, was both a wave and a particle. It could act like one or the other, depending on how you observed it. This duality wasn't just a strange trick of perception, it was fundamental to the nature of light itself. Imagine a ray of sunlight filtering through a window. It spreads and ripples like a wave, bouncing off dust and glass. But if you zoomed in very deeply, you'd find tiny quanta of energy, each with its own frequency, colliding with atoms, changing the world, one collision at a time. This idea of wave-particle duality is one of the strangest in all of physics, not because it's complicated, but because it defies the very categories we use to describe reality. In the classical world, things are either particles or waves, not both, not neither, and certainly not whatever they feel like being, depending on the situation. But the quantum world doesn't ask permission to make sense. Einstein's photon explanation for the photoelectric effect not only matched the experimental results, but did so beautifully. The energy of each photon depended on its frequency, just as Planck had suggested, and neatly explained why low-frequency light, no matter how intense, it couldn't eject electrons. Individual photons simply didn't have enough power. The impact of this idea was immense. In 1921, Einstein received the Nobel Prize in Physics, not for relativity, as many assume, but for his explanation of the photoelectric effect. That's how significant this discovery was. Still, even Einstein found the quantum world uncomfortable. He famously resisted the more probabilistic interpretations that would follow in later years. God does not play dice with the universe, he once declared, but data or not, the rules were changing, and at the heart of these changes was a strange truth. Light, the thing that illuminates our world, refused to fit into any neat box. It came in quanta, danced like a wave, collided like a particle. It flickered between states, revealing enough to keep us curious and enough to keep us uncertain. What began as a simple experiment with light and metal ended up shaking the foundations of physics. Because if light could behave this way, both continuous and discrete, picture this. You set up a table, place a flashlight on one end and cut two tiny slits in a piece of cardboard. You shine your light through the slits and watch the pattern the light forms on a screen behind them. Not exactly thrilling, right? And yet, in this humble arrangement, two holes and a little light, we find one of the most mind-boggling experiments in all of science. The double-slit experiment has become something of a legend in physics, and not because it's complicated. In fact, it's almost embarrassingly simple. But what it reveals is anything but. Some physicists have even joked that this is the most dramatic science experiment ever, starring a flashlight and two holes in a piece of cardboard. Let's start with what we'd expect. In the world of classical physics, waves and particles behave very differently. A wave, like water or sound, spreads. It interferes with itself. Imagine ocean waves passing through two openings in a barrier. The waves emerge on the other side and overlap, creating a pattern of peaks and troughs that can reinforce or cancel each other out. This is interference. It's well understood and predictable. Now, imagine particles like small rubber balls fired at a wall with two openings. Some pass through the left slit, others through the right. They don't overlap or interfere. On the screen behind the slits, you'd expect to see two clusters of impact points, exactly where the slits are. That's particle behavior. Simple, no surprises. So what happens when you do this with light? When scientists first shone light through the two slits, they expected it to behave like a wave. And that's what happened. The light scattered and formed an interference pattern, a series of light and dark bands on the screen, caused by the peaks of the waves overlapping and cancelling each other out at specific locations. So far, so good. The light, as Maxwell had predicted, was behaving like a wave. But then things got strange. Using highly sensitive equipment, the researchers dimmed the light source until it fired, just one photon at a time. Instead of a steady stream, individual particles of light were heading toward the slits, one by one. Now, would you expect these lone photons to act like particles, each passing through one slit or another? And if you wait long enough and collect enough impacts on the screen, there should be two bright spots where the particles landed, just like those rubber balls. But that's not what happened. Even when sent one at a time, the photons gradually built up the same interference pattern as before, a pattern that required waves to interfere with themselves. But how could a single photon interfere with itself? It passed through both slits. At the same time, it was somehow both a wave and a particle. At the same time, this was no illusion. The interference pattern persisted, suggesting that each photon had traveled through both slits simultaneously, like a ghost of itself, exploring every possible path until it landed. If that wasn't enough to raise eyebrows, things got even stranger. Physicists decided to peek behind the curtain. They placed detectors at the slits to observe which path the photon actually took. Surely, they thought, we can just observe and settle this once and for all. The photon passed through the left slit, the right slit, or somehow both. But when they looked, the interference pattern disappeared. As soon as the detectors were turned on and the photons were observed, the photons stopped behaving like waves. They acted like ordinary particles again, landing behind just the occasional slit. No more interference, no more ghostly wave behavior. It was as if the very act of observing forced the photon to make a decision whether to go left or right. Without overlaps, without uncertainties, reality had been caught red-handed and immediately righted itself. And it acted normally. Turn off the detectors, and the interference returned. Turn them back on, and it disappeared. The implications were stunning. It wasn't that our measuring devices disturbed the photons. They were passive, non-intrusive setups. The question wasn't how we observed, but that we observed. It seemed that the mere knowledge of the photon's path, the potential for knowledge, was enough to collapse its wave-like behavior. Reality, in a sense, cared whether it was being observed. This wasn't just a fluke or an experimental error. The double-slit experiment has been repeated countless times with photons, electrons, even molecules. Made of hundreds of atoms, the result is always the same. Left unobserved, these particles act like waves and interfere with each other. Observed, they behave like classical particles and align themselves in an orderly fashion. And if that sounds disturbing, well, you're not alone. This experiment is at the heart of quantum physics, and it resists all efforts to explain it within the confines of classical physics. Physicists soon realized that something fundamental was being revealed here. The act of observation, the act of measurement, was playing a crucial role in the reality of the universe. This is what's called wave function collapse. In quantum mechanics, a particle doesn't have a well-defined position or path until it's observed. Before being measured, it exists in a superposition of all possible states. When you observe it, it chooses a state. This means that reality, to some extent, is shaped by observation. What seemed like a static and fixed world in classical physics now reveals a fluid and uncertain nature. Quantum physics not only alters how we see matter, but also how we understand the very nature of reality. Imagine, for example, a particle in a box. Before being observed, it has a probability of being in several places within the box, all at the same time. When you observe the particle, it collapses to a single point, but until the moment of observation, we cannot know exactly where it is. This is what makes quantum physics so counterintuitive. In the macroscopic world where we live, we can predict and observe things with certainty. A soccer ball can't be in two places at once. But in the quantum world, this certainty disintegrates, giving way to probability. The famous physicist Niels Bohr was one of the first to accept this idea that observation not only reveals, but also defines reality. He suggested that the quantum world does not follow the rigid rules of classical physics, but rather a new set of laws where uncertainty is the norm. Bohr, and others like Werner Heisenberg, developed what we now call the uncertainty principle. This principle states that it is impossible to accurately and simultaneously measure certain properties of a particle, such as its position and velocity. The more precisely we try to measure one, the less we know about the other. This idea was disconcerting to many, including Einstein, who believed the universe should be more deterministic, governed by rigid and predictable laws. He resisted the idea of uncertainty and was famous for his quote, "God does not play dice with the universe." But experiments like the double-slit experiment continue to show that quantum physics was right, and there's no escaping this uncertain reality. Quantum physics doesn't give us certainties but probabilities. Particles can be anywhere until we measure them. This doesn't mean the universe is chaotic or random. On the contrary, it follows the laws of probability very precisely, but in a way that defies our intuition. The quantum world is not a random mess, but rather a field of possibilities that only becomes concrete when we observe it. This concept of uncertainty and probability was one of the great revolutions brought about by quantum physics. It changed the way we think about the universe. What we know for sure is that classical physics, as useful as it is in our daily lives, cannot fully explain what happens at subatomic scales. And this understanding that reality is shaped by observation was just the beginning of a journey that, to this day, continues to surprise and challenge us. The quantum world, full of uncertainties, probabilities, and mysteries, deviates from the laws we know and opens a new chapter in our understanding of the universe. Now, with these ideas in mind, let's pause for a moment to reflect on what all this means for our understanding of reality. What we know for sure is that quantum physics challenges our intuitive view of the world. The laws governing particle behavior are probabilistic, not deterministic. This means that rather than predicting a single outcome, quantum physics gives us only a probability of where a particle might be or how it might behave. The nature of the universe, then, is not something fixed and determined, but a web of possibilities that only become concrete through observation. In a sense, quantum physics suggests that reality isn't out there waiting to be discovered. It is created in part by the interaction between the observer and the observed. Until we look, the universe isn't defined. It exists in a state of superposition where multiple possibilities coexist simultaneously. This puts us in an uncomfortable position as it challenges the traditional worldview. In classical physics, things are either waves or particles. In the quantum world, the nature of what we observe depends on how we look. It's not a matter of a more complex explanation, it's a fundamental shift in how we think about the universe. Consider, for example, light. It can be a wave as demonstrated by Maxwell, or a particle as revealed by Einstein. This forces us to abandon the idea that light must be one or the other. In the quantum world, it can be both, depending on how we observe it. And the same goes for particles. Wave-particle duality doesn't just apply to light. It affects all subatomic particles, including electrons and even larger molecules. This creates a sense of fluidity in the nature of things. Unlike classical physics, where things are fixed and can be described in a well-defined way, the quantum world is much more flexible. This brings us to another interesting question: the role of the observer. The simple act of observation can alter a particle's state. This isn't just a peculiarity of double-slit experiments. In many quantum experiments, the presence of an observer can modify particle behavior in ways that cannot be predicted. The nature of quantum reality thus becomes not just a question of what is happening, but of how we are observing it. The presence or absence of the observer can determine the reality we experience, making the act of observation an essential factor in the behavior of matter. This raises a big philosophical question. If a particle's behavior depends on the observer, does that mean reality is not objective but subjective? Does that mean the universe exists only in potential until we decide to observe it? The answer is still unclear, but quantum physics definitely challenges traditional notions of objectivity. This indeterminacy can be disconcerting, but it also offers a new way of thinking. Rather than seeking a fixed, immutable truth, quantum physics suggests that reality is, in part, a field of possibilities, and our role, as observers is crucial to creating that reality. This doesn't mean that everything is random. On the contrary, probabilities follow very well-defined rules. The laws of quantum mechanics, while different from the laws of classical physics, are very precise. Uncertainty is not a flaw in the model, but a fundamental characteristic of quantum reality. In other words, what appears to be random is actually a manifestation of a set of possibilities constrained by precise laws. The quantum universe is not chaotic, but it operates on a scale where certainty is not guaranteed and the future is not rigidly predetermined. This also raises an interesting question about the future of quantum physics. If observation influences the behavior of particles, does this imply that there is some kind of interaction between human consciousness and the quantum world, or more broadly, between the observer and the universe? The question of how human consciousness relates to the quantum world is still far from resolved, but it is certainly one of the great mysteries of modern science. Many scientists grapple with it as they try to understand the role of the observer in quantum mechanics and its deeper implications. For now, what we know is that quantum reality cannot be fully understood with the logic and tools of classical physics. It challenges our expectations and forces us to reconsider everything we know about the universe, how it works, and most importantly, how we observe it. And if that weren't enough to change our worldview, quantum physics presents us with another, even more surprising phenomenon: quantum entanglement. This is one of the most fascinating and at the same time most difficult concepts to understand. Entanglement occurs when two particles become interconnected in such a way that the state of one of them cannot be described independently of the state of the other, even if they are separated by great distances. A particle can be entangled with another so that, by measuring one of them, you instantly determine the state of the other, regardless of the distance separating them. Imagine two entangled particles. If you measure the spin of one, you'll automatically know the spin of the other, even if it's on the other side of the universe. Sounds impossible, right? After all, according to classical physics, nothing can travel faster than light, not even information. This instantaneous connection between particles, called spooky action at a distance by Einstein, profoundly challenged the physics of the time. If particles can influence each other instantaneously, it means that communication between them occurs faster than the speed of light, which conflicts with the theory of relativity. The concept of quantum entanglement was demonstrated experimentally in a series of experiments, most notably by physicist Alain Aspect in the 1980s. He managed to show that quantum entanglement was not an illusion, but rather a real feature of subatomic particles. Despite the phenomenon's strangeness, it has been confirmed in several subsequent experiments. Quantum entanglement has become one of the cornerstones of modern physics and is being exploited in emerging technologies such as quantum computing. But what exactly is going on here? How can one particle know what's happening to another, even at such a great distance? The answer, according to quantum mechanics, is that entangled particles share a deeper connection beyond traditional space-time. In other words, they are linked in a way that cannot be described by classical physics. Quantum entanglement suggests that particles may be connected by an invisible network, a network that transcends the concept of space and time as we know them. This phenomenon raises profound philosophical and scientific questions. What does it say about the nature of reality? If particles can be connected instantaneously, this implies an underlying structure to space-time that we don't yet fully understand. Some scientists have proposed that quantum entanglement could be a clue that space-time as we understand it is not fundamental, and that the true nature of reality could be something more fundamental, transcending our current notions of space and time. A full explanation of quantum entanglement and its implications is yet to come, but it is a phenomenon that continues to challenge our most basic notions of how the universe works. It calls into question the separation between objects, the speed of information, and even time itself. In practical terms, quantum entanglement is being used in quantum computing, the ability to process information in entangled states could enable the creation of computers much faster and more powerful than any classical computer. However, the fundamental question of what entanglement tells us about the nature of reality still remains. If particles can be instantaneously connected in ways that defy relativity, what does this mean for our understanding of causality and information in the universe? Quantum entanglement remains one of the greatest mysteries in modern physics, with many unanswered questions about what it actually implies for the fundamental structure of the universe. But what is certain is that as quantum physics advances, quantum entanglement will continue to be one of the pillars that support the exploration of new technologies and the search for a deeper understanding of reality. Quantum computing is one of the most exciting fields in modern physics, and it is directly based on the fundamental principles of quantum physics. Unlike classical computers, which process information in bits, quantum computers use qubits, units of quantum information that can represent multiple states simultaneously. The key characteristic of a qubit is its ability to be in a superposition of 0 and 1 simultaneously. This is possible thanks to the phenomenon of quantum superposition, which allows the qubit to exist in a combination of states until measured. This property is what makes quantum computers so powerful. In a classical computer, a bit can be either a 0 or a 1, but in a quantum computer, a qubit can be either a 0, a 1, or any superposition of both, exponentially increasing information processing capacity. This allows quantum computers to perform complex calculations much faster than traditional computers. Imagine solving a problem that requires searching for multiple possible combinations. On a classical computer, you would need to test each possibility one at a time, but a quantum computer can explore multiple possibilities simultaneously thanks to superposition. This makes quantum computing especially powerful for tasks like code breaking, molecular simulations, and process optimization, tasks that are extremely difficult or even impossible for classical computers. Quantum computing has the potential to revolutionize several industries, including pharmaceuticals and cybersecurity. However, there are significant challenges to overcome before quantum computing becomes a widely accessible technology. The main difficulty is maintaining quantum coherence, which is the ability to maintain the superposition of qubits without them collapsing due to interactions with the environment. This problem is known as decoherence, and it's one of the biggest obstacles to building practical quantum computers. Scientists and engineers are working hard to develop ways to preserve quantum coherence for longer periods of time, which is essential for performing long-term quantum calculations. Furthermore, another important issue is quantum error correction. Unlike classical systems, where error detection and correction are relatively straightforward, quantum systems are much more susceptible to errors due to the probabilistic and delicate nature of qubits. Despite these challenges, progress has been impressive. In recent years, companies like IBM, Google, and others have been developing increasingly powerful quantum computers. Google, for example, announced in 2019 that it had achieved quantum supremacy, a major milestone in which a quantum computer accomplished a task that would be virtually impossible for a classical computer. Quantum supremacy was a major step forward for quantum computing, but we're still far from seeing quantum computers in everyday use. The potential to accelerate scientific discoveries, optimize industrial processes, and solve complex problems is enormous, but the technology needs more time to mature. One of the most exciting areas of quantum computing is quantum simulation. Many complex questions, such as the behavior of molecules at a quantum level, are extremely difficult to study with classical computers. Quantum computing could change this, enabling more accurate and faster simulations. This could have a direct impact on the development of new drugs, materials, and technologies, potentially accelerating innovation in fields such as medicine and engineering. Imagine being able to simulate and understand molecular interactions much more effectively, creating new substances with precision. However, quantum computing is still an emerging field. The technology is advancing rapidly, but there are many hurdles to overcome before it becomes widely available. In the future, we may have quantum computers operating alongside classical computers, offering specialized solutions for tasks that require immense computational power. For this to happen, a significant leap forward in the infrastructure and design of quantum systems will be required. Furthermore, the development of new quantum algorithms that can take advantage of the unique nature of qubits to solve problems more efficiently than classical methods will be crucial. Although quantum computing is still in its early stages, it represents a revolution in the way we process and manipulate information. The potential is nearly limitless, and the coming years will be crucial in determining how this technology will shape the future of science, industry, and society as a whole. As we delve deeper into the mysteries of quantum physics, we are confronted with paradoxes that defy our understanding. One of the most famous is Schrödinger's paradox, which presents a seemingly absurd situation that illustrates the strangeness of quantum mechanics. Schrödinger's thought experiment involves a closed box containing a cat, a vial of poison, and a radioactive device. According to the laws of quantum mechanics, until the box is opened, the cat is simultaneously alive and dead. It exists in a superposition of both states. This paradox isn't meant to suggest that cats can be both alive and dead at the same time, but it illustrates the peculiar behavior of subatomic particles. As long as the box is closed, the system, cat plus poison, is in a superposition of states, until an observer collapses this superposition into a single, defined state. Schrödinger's paradox was one of the first examples of how quantum mechanics deals with situations of uncertainty and superposition. And, although it was formulated as a thought experiment, it reveals a crucial point. The act of measuring, of observing, can alter the state of a quantum particle or system. This concept of superposition isn't limited to thought experiments. It's fundamental to many current quantum technologies, such as quantum computers. The idea that particles can exist in multiple states simultaneously is what allows quantum computers to solve problems much more efficiently than classical computers. Schrödinger's paradox is just one of many that arise when trying to apply quantum mechanics to the macroscopic world. In many cases, the rules of quantum physics seem to conflict with our real-world intuitions, and this raises the question, how should we understand quantum reality? Another famous paradox is the double hole, which we discussed earlier, where particles appear to act as both waves and particles at the same time. This suggests that the laws of classical physics cannot fully describe reality at microscopic scales, and that the true nature of the world may be far more complex than we imagine. These paradoxes have no easy answers. They force us to reconsider our ideas about reality, time, and causality. If particles can be in two places at once, or act as both waves and particles, it means the quantum universe operates by different rules than those that govern the macroscopic world. Quantum physics tells us that the world is not as clear-cut and determined as it seems. Uncertainty is a fundamental principle of reality, and observation plays a crucial role in defining what is real. This challenges our classical view of a rigid and predictable universe, replacing it with a world where probability and uncertainty dominate. For many physicists, these paradoxes are more than mere curiosities. They are an opportunity to reimagine what reality means. Quantum physics presents us with a universe in which observation and measurement are essential parts of the very fabric of the cosmos. This leads to one of the biggest questions physics still faces: what is truly real? Subatomic particles can exist in a variety of states simultaneously until they are observed. But does this mean that reality is subjective, dependent on the observer? The nature of our reality remains one of the greatest mysteries in physics. Although quantum mechanics has been confirmed by numerous experiments, its philosophical implications are profound and still not fully understood. Schrödinger's paradox and other quantum problems continue to challenge scientists. Studying such paradoxes is crucial to the advancement of quantum physics, but it also requires us to rethink many of our most fundamental beliefs about the world. Perhaps in the future, the answers to these questions lie in more advanced theories that we are still far from discovering. What is certain, however, is that quantum physics is not just a scientific curiosity. It has the power to change everything we know about the universe, from the nature of reality to the laws of physics themselves. Each paradox, each mystery, pushes us toward a deeper understanding of existence. Ultimately, quantum physics not only reveals how the universe works at the subatomic level, but also forces us to confront our own ideas about the nature of reality, time and causality. And perhaps in the process, it helps us better understand ourselves and our place in this vast cosmos. Quantum physics is still in its early stages, but it has already changed our worldview. And as we explore this vast field, new questions, new technologies, and new paradigms emerge. The future of quantum physics promises to be as fascinating as its past, if not more so. In the coming years, we can expect major advances in areas such as quantum computing, quantum cryptography, and even the simulation of complex quantum systems. Quantum technology has the potential to revolutionize entire industries, making calculations and simulations possible that seem impossible today. One of the great promises of quantum physics is its application in fields such as medicine and pharmacology. Quantum computing can be used to model complex molecules, accelerating the development of new drugs and treatments. Furthermore, simulating quantum systems can lead to advances in new, more efficient materials. Another area of great interest is quantum cryptography, which can provide an unbeatable level of security. With quantum computing, it is possible to create communication systems that are, in theory, impossible to hack. This could protect extremely sensitive information, from banking data to state secrets. Furthermore, quantum physics can help solve fundamental problems in physics, such as the unification of the forces of nature. Currently, modern physics is divided between general relativity, which describes gravity, and quantum mechanics, which describes the other fundamental forces. The unification of these theories would be one of the greatest achievements of science, but quantum physics also raises important philosophical questions. If reality is shaped by observation, does that mean we are somehow creating the universe as we observe it? If particles can be in multiple states simultaneously, what does this mean for the nature of time and causality? These are questions that scientists and philosophers will have to address in the coming years. Quantum physics is not just a technical field. It forces us to reimagine our deepest beliefs about the universe and our place in it. And as we advance in the study of the quantum world, we can expect new answers. As quantum technology advances, we will also be able to develop new tools to explore the nature of reality. Perhaps one day we will uncover the underlying quantum paradoxes, such as entanglement and superposition, and better understand how these ideas fit into a unified theory of the universe. Quantum physics, with all its oddities and paradoxes, is just the beginning. As we explore the behavior of subatomic particles more deeply, more discoveries will be made. What seems incomprehensible today may soon be the key to understanding what's really happening at a fundamental level. The future of quantum physics is bright and full of possibilities. We don't know exactly where it will take us, but one thing is certain: quantum physics will continue to challenge our perceptions and expand our understanding of the universe in ways we never imagined. What we know for sure is that the future of science will be quantum. Quantum physics is poised to transform every aspect of our lives, from technology to the way we understand reality. If scientists can overcome the technical challenges of quantum computing and other technologies, the quantum revolution will be a historic milestone similar to the Industrial Revolution, but with an even more profound impact on our society. The true impact of quantum physics, however, may not be just technological. By challenging our ideas about what is real, it could also profoundly alter the way we see the world and ourselves. And perhaps the greatest impact of all is forcing us to embrace the uncertainty, randomness, and complexity of nature, helping us build a world more open to possibility and discovery. The future of quantum physics is just the beginning of an exciting and mysterious journey. What we discover in the coming years could help us understand not only the universe, but also the nature of our own existence,